So welcome everyone. My name is Sigrid Elt. I'm from Ericsson, Mälardalen University and Cotton University. And I welcome you to this session on code smells and clones. And we have a busy program with fantastic speakers. Our first speaker is Yuekun Wang from University of Science Technology of China. And he has a lot of co-authors. I get him to present them. And the first paper is Comparison and Evaluation of Clone Detection Techniques with Different Code Representations. Welcome. We warm up after lunch, right? So questions after, please think of good ones.
Hello everyone, this is Yuekun Wang speaking. It's my great honor to introduce our work published in ICSE 2023 to all of you. The work is entitled as Comparison and Evaluation of Clone Detection Techniques with Different Code Representations. In today's increasingly prosperous open source community, code clone detection is particularly necessary. First, cloning code is a very common phenomenon in software development. And programmers usually copy and paste some existing code to improve efficiency. But the existence of code clones will lead to certain risks. Code clones may cause vulnerabilities propagation and increase the maintenance of software systems. In addition to clone management, clone detection can also be applied to license violations and mining new candidate libraries. In view of the necessity of clone detection, many researchers are currently working on developing more advanced tools. The workflow of these clone detection techniques is roughly as follows. First, pre-processing a given code base and get code fragments, then perform feature extraction to obtain intermediate representation for further similarity comparison. Finally, report all clone candidates for users. Besides, according to different intermediate representations, code clone technique using source code text content for similarity comparison is classified as text-based, and using token sequences as token-based, using abstract syntax trees as tree-based, and using control flow graphs or program dependency graphs as graph-based. Among the existing clone detection techniques, it is generally believed that graph and tree representations have better detection capabilities, because they contain semantic and structural information of the source code. But there is a lack of clarity on the capabilities of clone detection techniques. In general, code clones can be divided into 4 types, type 1 to type 4. The first 3 are syntactic clones, and type 4 is a semantic clone. Study has shown that type 3 clones account for a higher proportion in some open source software systems. Therefore, if we can obtain the distribution of clones in the real world, it will help researchers to conduct more targeted research. For example, if most clones have simplicity, there is no need for us to design an overly complex tool. And as the code size increases, large-scale clone detection is especially necessary. In heavy text, text-based and token-based techniques are more lightweight, but less accurate. So we want to know how to combine the advantages of techniques based on different representations. And to fill current research gaps, our work mainly answers the following research questions. RQ1, which code representation is more effective in clone detection? And RQ2, what is the distribution of different clone types in open source community? and RQ3, how to combine different methods to achieve efficient and effective large-scale clone detection. For RQ1, we conduct an empirical study. We reproduce 12 algorithms and measure their recall on big clone bench. For RQ1, we reproduce 12 algorithms based on different reputation and grouped them into 3 categories, just like this. For the convenience of comparison, we classify text and token that do not contain synthetic information into one category. For the dataset, we use the very popular benchmark, big clone bench. In big clone bench, clones between type 3 and type 4 are again classified according to synthetic similarity. That is very strong type 3, moderate type 3, and weakly type 3 or type 4. But such classification is still too coarse, and the basis of classification does not contain structural information or synthetic information. Therefore, we propose TreeDiff to describe the difference between ASTS of 2 code fragments, and then combining the synthetic similarity of big clone bench, we can get the average diff that considers lexical information and synthetic information. We experimented with 12 different algorithms on big clone bench and combined the clone results by groups. Table 1 shows the recall results on the classification of big clone bench, and the figure 1 shows that the recalls of our proposed final grand classification. The results shows that token and tree representations perform better in very strong type 3, and moderate type 3 clone detection, while graph representation performs better in weakly type 3 or type 4 clone detection. This is because the graph will retain more semantic information in the code, but at the same time, the tiny addition or deletion of method calls will also have a great impact on it. And we can find the threshold of the 3 diffs when graph representation algorithms are more efficient in figure 1. As for RQ2, we mine clones of the simple set and verify manually to get the distribution. Getting the clone distribution first requires mining all clones, but the determination of clones is inevitably subjective, especially semantic clones. So the alternative is to use tools to mine as many clones as possible and vary them manually. Our simple set is taken from IGA dataset. IGA dataset is crowd from well-known open source software platforms, such as Google Code and SourceForge. And this repository contains more than 2 million Java files, so it can represent the actual code of open source community to a large extent. Figure 2 is the cumulative distribution function graph of clone pairs, and table 2 records some important points in the left graph. And we can see the difference value of most type 3 clone pairs are relatively small. This means that most clone pairs belong to simple code clones. And according to the result of RQ1, we find that most clones are in the range that token and tree representation can detect. Based on the results of RQ1 and RQ2, we select the best combination of different algorithms to answer RQ3, and then develop it as a tool. Since most clones are relatively simple, we choose to give up heavy graph-based algorithms. We combine the different token-based and tree-based algorithms and selected the most suitable one. and finally developed it into a tool called TACC, a token and AST-based code clone detector. And this is the overview of TACC. The core idea of TACC is to use efficient token-based algorithms as a filter for clone candidates, and then use accurate tree-based algorithms as the final verification. In this way, TACC not only maintains high efficiency, but also ensures effectiveness as much as possible. And finally, we evaluate our tool. We comprehensively compare TACC with other state-of-the-art tools in terms of effectiveness and scalability. The results are shown in tables. TACC achieves the best recall among all tools while maintaining high precision, especially in the detection of very strong type 3, and moderate type 3 clones. This is due to SDL algorithms in the verification phase. In addition, the runtime overhead of TACC is also excellent, only behind NIL. Due to the token-based filtering, TACC has the ability of large-scale clone detection, and our tool is available on this site. In the end, I will summarize our work. At first, we reproduce 12 clone detection techniques with different code representations on a unified platform and conduct an empirical study to figure out which code representation is more effective in detecting clones. Number 2, we propose tree-diff and perform fine-grained division of real-world clone types. After manual analysis, we observe that most type 3 clones have simplicity. And at last, we conduct different combinations of different clone detection algorithms and find out a suitable one. We implement it as a tool named TACC, which can achieve ideal performance. And thanks for your listening.
Thank you. Questions? Yes, please. Come up here to the microphone.
Thank you. I want to know, how do you choose and combine your lots of algorithms? In other words, I don't understand your concrete combination method. Thank you.
Oh, thank you for your question. This solution to the problem has a comprehensive experiment in our paper, but because of the time constraint, I'm sorry about that I can't present this content on slides. Our main method is to measure the recall of different combinations. For example, because token-based algorithms are lightweight, so we chose them as the filtering. And the tree-based algorithms are more accurate, so we chose them as the verification. So then we measure the recalls of each group of them and choose the best one from them. Besides, we will adjust the token-based algorithm, the threshold of the token-based algorithm to achieve filter out as candidate as many as possible. And on the other hand, to make sure it won't figure out the clones that tree-based algorithm can detect. That's all.
Okay, thank you for your answer.
Hi. One of the problems with static analysis tools such as Covariety or Clockwork is that in order to get enough good ideas of real problems in the code, you have to tune the parameters so that you get a huge number of results, many of which are false positives. Do you have an idea about which clones or when clones are likely to be problematic and when maybe they represent a good design decision or a reasonable one and you don't want to remove them? And if so, can you look for or somehow adjust the tuning so that you only get problematic clones?
You mean that how to judge the clones whether it's meaningful in the software?
Not whether it's a clone, but whether it's a problematic clone. So people use copy-paste all the time, and sometimes it's a reasonable decision.
Because the determination of clones, it has accompanied the subjective, the semantic clones. You will be think this is a clone, but I won't think this is a clone. So judge the clone if it's the problem clone maybe challenging. So
okay, thank you.
Future work, right? Okay. Last question. We move on.
Yes.
Okay.
Thank you for the previous question. It's interesting. I have a question about the way we use the datasets. So I look at the recent study focusing on the code representation. They use the very old and small dataset like Big Long Bench or ITGA or on the one you use. Maybe the other one is online just datasets. So all of them is very small and old dataset and just have few lines of code for each data point. So think about when you apply your research into the practical dataset, like code from industry is more structured, more difficult, more complex. What do you think about the performance or the impact of your research on that? Do you have any plan to apply the more complex dataset into your research? And if the question is yes, so how do you have any idea on how do we expand the methodology into the practical dataset?
More complex the dataset, you mean that type 4 clone dataset. Our work is mainly focused on traditional clone works, and type 4 clones is suitable task for machine learning or deep learning towards the work. But this kind of tools usually can't be applied in a very large open source community. They are how to explain?
Not yet, right? But you haven't looked at it, so okay.
Yep.
I think we need to cut there and thank again Yuang from this. Yeah. So we move on to the next speaker, I think, magically. And I would like to welcome the next speaker. So now here we go. And now I lost everything. So Jiahao Liu for learning graph-based code representation for source-level functional similarity detection. So it's another way to look at code representations. Welcome very much.
Thanks for the introduction. Hi, everyone. I'm Jiahao. It's my pleasure to present our work, learning graph-based code representations for source-level functional similarity detection. This is a joint work with Jun, Xiang, and Zhenkai. Let's first discuss the problem of code functional similarity detection. Given a code fragment C star and a corpus of code fragments C, including C1, C2, and so on, the question is how to identify candidates in C that are functionally similar with C star. For example, given a code fragment is factor which decides whether B is a factor of A. The question can be formulated as, can we find the code fragment doing the same thing in the code base? We know code functional similarity detection is a cornerstone of various software engineering tasks, such as code clone detection, code classification, code search, and bug detection. So how does previous work detect similar codes? According to the code interpretations, we categorize them into 3 classes. First is token-based methods. This kind of method treats source code as a token sequence. However, the token sequence lacks of program structures, so it is hard to detect textually different and structurally similar code. The second research direction is tree-based methods. This kind of method treats source code as an abstract syntax tree. However, the abstract syntax tree is agnostic to program semantics, so it is hard to detect semantically similar programs with different syntax. To integrate program semantics, graph-based methods integrates control flow and data flows. However, previous work mainly focused on the local information. Here, it means they mainly focus on the one-hop or two-hop information in the graph representation. So they may lack of overall graph structures. Based on this, we aim to design a new approach to learn graph-based code representation for source-level functional similarity detection. To do this, we need to answer 2 questions. First, which code representations should be used to comprehend programs? We know abstract syntax tree can well describe program syntax. Control flow graph and data flow graph carry semantic information. So, combining abstract syntax tree, control flow graph, and data flow graph together as a joint code property graph can benefit the program understanding. The second research question is how to capture useful information from the code property graph for similarity detection. We find graph neural network is powerful at capturing graph structure features. However, graph neural network is not originally designed for program analysis. So, tailor a graph neural network to learn graph-based code representation for similarity detection is promising. Based on this, our goal is to customize a graph neural network on code property graph to facilitate functional similarity detection. Based on this, we propose tailor to learn graph-based representations for similarity detection. We can see this is the overview of a tailor. It first transforms code fragments into code property graph, and then it views model code representations with CPG-based neural network. In the end, it will provide detection signals about code functional similarity, such as code clone detection and code classification. In our design, we take the classic code property graph definition. The code property graph integrates abstract syntax tree, control flow graph, and data flow graph. In our design choices, we first extract the abstract syntax tree as the basis for generating other code representations. Then we identify the control flow graph by analyzing control flows in one function and the invocation across different functions. Then we identify the UDEF variables in code segments to form the data flow edges. In the end, we will unify abstract syntax tree, control flow graph, and data flow graph into the code property graph. And the nodes in the code property graph are the same with the AIT nodes. And the edges include AIT, CFG, and DFG edges. Having obtained the code property graph, we need to extract useful information for similarity detection. And our key idea is to design a graph neural network tailored to learn code representations for functional similarity detection. Given a CPG node, we first fuse type and token features to represent CPG nodes. We know type and token symbols can carry syntactical and semantic information in the program. So we first employ word vector to embed type and token symbols into the word vector space. And then we combine type and token embeddings to generate the code property graph node embedding. After that, we propagate node embeddings along code property graph edges to learn graph structures. Here, one question comes up: why we need to learn the graph structures? That's because graph structures can enrich node semantics and contexts in the code property graph. For example, this is the multi-hop path from the code property graph. From the multi-hop path, we can know identifier A is used as a function argument in the program. So we propagate neighbor information along the CPG paths. Having obtained the information passed from the neighbors, we update node embeddings with this neighbor information. Generally, there are several technologies can be used to do the combination. Recent studies often use the GRU from off-the-shelf GGNN. We know GRU is designed for solving the gradient vanishing problem. And in our empirical evaluation, we find that 4 iterations is enough to capture features for functional similarity detection. So it will not appear the gradient vanishing problem. If we use the GRU directly, it may increase the training difficulty or degrade the GNN's performance. So in our design choices, we combine the node embedding and neighbor embedding directly with the trainable metrics to extract important information for functional similarity detection. Then we stack multi-hop neighbor information. Since neighbor information at different hops describes global graph structures. And in our design choices, we combine multi-hop neighbor embeddings to generate the final node representations. Now the node representation of the code property graph have captured the overall graph structures. To produce neural representations for a code fragment, we combine its CPG nodes using the pooling operations. With the neural representations, we can use it to do code functional similarity detection. For code clone detection, we calculate the distance of code representations to infer clone pairs. For source code classification, we apply fully connected layers to classify it into different categories. To evaluate the performance of a Taylor, we test it on 2 different datasets. First is OJ clone. OJ clone is constructed from 52 thousand C programs, and these programs belong to 104 tasks. We use it to do code clone detection and source code classification. Another dataset is Big Clone Bench. This is a popular code clone benchmark, and it is constructed from 25,000 Java systems. We use it to do code clone detection. To evaluate a Taylor, we answer the following research questions. First, how effective is Taylor in code clone detection and classification? Third, second, how does CPGN contribute to Taylor compared with over-the-shelf GNNs? Third, to what extent do different design choices of CPGN affect Taylor's performance? For the first research question, we compare Taylor with state-of-the-art methods on code clone detection and source code classification. The code clone detection results are summarized in the following table. Note that we didn't evaluate every approach in the 2 datasets, since some approaches are designed for particular programming language. For example, FCD detector is designed to detect C similar codes. From the table, we can find Taylor achieves the better performance than other token-based, tree-based, and graph-based methods. For the source code classification results, we can find Taylor also achieves the better performance than other tree-based and graph-based methods. So we can conclude Taylor achieves state-of-the-art performance in functional similarity detection. We also compare different over-the-shelf gene variants on OJ clone dataset. The results are listed in the following table. We can find here, CPGN-NP means we disable the propagation mechanism in the CPGN. From the table, we can find CPGN achieves the best performance than other GN variants. We also visualize code representations produced by CPGN-NP, GCN, and CPGN. Here, why we choose CPGN-NP and GCN, that's because the CPGN-NP achieves the worst performance, and the GCN achieves the second best performance. From the figure, we can find CPGN achieves the best performance. For the samples in the same cluster, the samples are closer to each other, and for different clusters, CPGN can achieve clear boundaries. So we can conclude CPGN shows the strongest capability to model code representations. We also investigate the effect of embedding initialization, code property graph representation, and CPGN layer number. From the table, we can find node type and token both contribute to learn code representations. And the code property graph provides a comprehensive view of programs. Also, including multi-hop neighbors is beneficial to understand the programs. To conclude, we propose Taylor. It can learn high-quality graph-based code interpretations, and we use these code interpretations to do code functional similarity detection, such as code column detection and source code classification. And our insight is code property graph can carry essential information to present program syntax and semantics. And we can customize a graph neural network to learn graph-based code interpretations by propagating node information along CPG structures. And now our artifact is available on the GitHub repo. That's all. Thank you. I'm happy to take questions.
Yes, thank you.
Hello, thank you for your presentation. My question is regarding your data sets. So you use OJ, clone, and BCB.
Yeah.
But your goal is to detect semantic clones. These two data sets, as far as I know, are they purely type 4 clone based? Because BCB has other clone types. So wouldn't it be more appropriate for you to evaluate your tool on a data set that has purely semantic type 4 clones, like, for example, semantic clone bench?
I think in our evaluation for the OJ clone, it is collected from the online data systems, and they have about 104 tasks. In each task, these programs are doing the same task, and they have the same functionality. And we assume, following previous work, we assume they have the same semantics for it. Also, for the big clone bench, we also evaluate the results on the type 4. They are type 4 code clone. And the type 4 should be semantic similar programs. Also, I think maybe we can, in the future work, we can try to evaluate our tool on purely semantic data set.
Maybe thank you.
Yeah, okay, thank you.
Hi, thank you very much. Okay. I have a question about your last claim. How do you customize the GNN? It appears you're just applying a GNN to a PDG. How are you exactly customizing it to the PDG?
Yeah. I can get your point. So we find that in program analysis, lots of approaches just use graph neural network directly without any justification. For example, in vulnerability detection tasks, they maybe just use the GNN directly to find the vulnerability in the code. And we find that if we use it directly, and there may be increase the training difficulty and decrease the training the performance. And we try to justify every component of the graph neural network. For example, how to combine in our talk, how to combine neighbor information and self-interpretation together. We don't use off-the-shelf GNN's GRU, and we just combine it and with the tremor metrics. This is very simple, but it achieves better performance on it, and the training difficult, and the training is very easy about it, using it.
Thank you.
Yeah.
Okay, thank you very much. Thank you. Good job. Good job. Now we're going to hear about the Smelly 8 collaboration between Irvine in US and Lisbon, Portugal, and Porto, right?
Yes.
And I hope we know. There we go. Oops, I'm going away. And we're Effectar going to present this. I can't pronounce it. Sorry.
Thank you. Thank you for the intro. So hello and welcome everyone. So my name is Iftikhar, not whatever was said before. So today, thank you for joining the talk. I'll be presenting the Smelly 8, an empirical study of prevalence of code smells in quantum computing. So I'm an assistant professor at UC Irvine, and this was a collaboration between UCI and University of Lisbon and University of Porto. The first author, Chi, could not be here because of visa issues, so I'll be presenting to the best of my ability. So before we go into the details, let's have a quick background. So what is CodeSmell? So CodeSmell is something that was initially designed and developed to identify implementation incorrect choices or design and implementation flaws that were necessarily not an immediate concern, but that would become a concern down the line. And that would lead to maintenance issues, developer productivity, and even association with bugs. And a lot of work has been done in terms of CodeSmells with regards to different programming language, different association with different quality aspects of software. Now, another piece of background, which is very relevant to this talk, is quantum computing. And as we all know, quantum computing is one of the next up and big things, and because of its potential for solving computational heavy problems, because it is able to deal with binary qubits simultaneously, 0 and 1 at the same time. And intrinsically, this is different from the traditional programming that we do. And also, of course, it's becoming more and more important because with time, as you can see on the right bottom left corner, the number of systems using or relying on quantum programming is increasing over time. So because of that, it is important to start looking into it. And also, another piece of background that we should be aware of, at least from a software engineering perspective, again, from 30,000 feet, is what is the difference between the programming that we do and versus quantum programming. So one difference is obviously in terms of the basic unit. We are used to bits, zeros and ones, whereas in quantum, it's more on qubit, where you can do it simultaneously. And then in terms of information manipulation, we are used to logic gates. In quantum, there are quantum gates. And the next one, which is more important for our purposes, is in regular programming, whenever we store a value, we can assume that it's going to be there until the execution ends. But that may not be true in quantum because the value could decay or it could even vanish. So it's more unstable compared to regular programming. Now, that's where we got interested because how good are we doing, or do we even have tools and mechanisms to identify these smells? So when we looked into literature, we really didn't find any papers that looked at quantum-specific code smells. There were papers that looked at traditional smells and tried to find them in quantum programs, but not quantum-specific smells. And because quantum programming is different from traditional programming, there are going to be unique smells that we should look for. And obviously, there were no existing tools for identifying these smells. So I'll quickly go through the methodology to give you an overview of the steps that we did. So we first started by looking at the best practice that Google has put out for quantum programming. And analyzing that, we identified 8 quantum smells, or the opposite of best practices from analyzing the best practice. And then, of course, we were not the experts. At least 3 of the authors were not experts of quantum programming. So the goal was to get some feedback from the real quantum developers. So we conducted a survey. And we sent out the smells that we identified or defined to 35 quantum developers. And we asked them whether they agree with our definition and whether they think this smell that we are identifying, does it have any severity, how difficult it is, all of those kinds of questions. We asked them about those. Now, as I mentioned, one of our goals was to build a tool and evaluate it on some data set. So we needed to collect or curate our data set because no such data set existed. So we started by going to the obvious place, GitHub. We looked for Python projects that uses Qiskit library. The reason we selected Qiskit is because it's one of the most frequently used quantum libraries or frameworks, so we selected that. We searched and found 628 projects, not so much. And then, of course, we did the obvious filtering, right? Removed projects that did not have a lot of commits, that gave us 21 projects. Then we removed projects that were tutorials and lecture notes, so it gave us 3 projects. So now within these 3 projects, there were 17 programs or quantum programs Out of those, since we needed to evaluate our tool, which we will be building, which I'll be talking about in next slide, and I don't know what's happening. It's just going by itself. Okay, so we had to create a benchmark data set, so we picked two, randomly picked two, and we manually labeled those two programs. So then we built QSmell, which is our tool for identifying the quantum smells. And we focused, as I mentioned, focused on Qiskit. And we had to rely on a combination of static and dynamic analysis because some of the smells needed to identify the functions that are being called, the parameters that are being passed, those kind of information. So we needed to traverse the AST. And then there were some smells which needed dynamic analysis. And for doing dynamic analysis, what we essentially needed is the state of the qubit and execution metrics, which you can get using the library Qiskit provides, an API Qiskit provides. So here you can see the table of the execution metrics. And here, each row represents the qubit, and each column represents time snapshot, right? Every time snapshot, what is the state? And it again just went back by itself. Right, and every cell represents the operation that has been performed or that is taking place on the qubit in that moment. So then we executed or evaluated our tool on the benchmark data set. And we had very high precision recall and F1 because it's a combination of static and dynamic analysis. And also, we had only two projects in there. The projects that we ran our tool on, the quantum programs, the 15 that we had set aside, on an average had 229 lines of code for qubits and 1130 operations. So these are the two research questions that then we were able to answer, which related how do practitioners perceive quantum code smells, and what is the prevalence of quantum-specific code smells in programs. So this is the result that we got from the survey. So as you can see, IDQ, which stands for idle qubits, is the most perceived one according to the developers. And to give you context, IDQ stands for you assign or initiate a qubit, and then you don't do any other operation on it for a long time. So that's idle qubit. And the CG is customized gate. And customized gate indicates that instead of using a library function, you are using something written by yourself. So that was from developers' perception survey. And then when we ran our tool on the 15 programs, this is the result. And as you can see, long circuit, non-parameterized circuit, and idle qubits, the one that I just talked about, were the three most frequent smells. So we'll talk about long circuit and idle qubit in a sec. So long circuit smell is essentially what it means is your circuit size should be as short and as short as possible instead of being long and too deep. Because if it is long and deep, then the probability of error increases. So you try to keep it as short as possible. So here is an example. If you look at line 2, you'll see that we are initializing a circuit, and then we are doing three operations, operation H, Z, and H on that circuit. Now this is a smelly one because the circuit is actually not quite, but it's long, and it's a simplified example. Now, if we want to smell free it, then this is one way of writing it, where we are actually combining operation H, G, and H into that operation X. And the figure below is a graphical representation of what that circuit looks like. So that was one of the most prevalent ones, long circuit. Then the next one was non-parameterized circuit. Again, so here the main idea is you want to reduce the number of communication with backend as much as possible. So you try to parameterize the function call so that you don't have to call back and forth. So here is an example, and again, no need to pay attention to this code snippet here, is just initializing a circuit. And again, no need to pay attention to this one. And this is the graphical representation of what that circuit looks like. So once you have this circuit, that's when we can actually look for the smelly examples. This is one Smelly example, and if you pay attention, you'll see that we are calling the circuit, in each circuit, the function that I just showed you, we are calling it inside a for loop again and again and again, right? So it's not the optimized way. Whereas, what you can do is you can actually do the binding and then call that circuit just once, or communicate with the backend only once instead of going back and forth. So that's non-parameterized circuit. So, and that was all we did. And again, of course, I gave details from very 30,000 feet overview-ish for the sake of time. So if you're interested, please have a look at the paper. Thank you.
Excellent job. And I think it's not enough quantum programmers yet. It's kind of new, so it's very seminal what you do. So thank you. So do we have any quantum experts here in programming? That's the problem, though.
Yes. So that's essentially one of the problems that we had to do such like international collaboration to find experts of quantum, who, by the way, is not here today.
No. But it's a very interesting area, and it's moving, as you say, super fast. Right. So I really look forward to hear more, because I think also having this guidance very early from you will help the future programmers. So I assume this tool is
it's
available.
Online.
And you're going to do more teaching on how to really write those programs effectively. Okay.
Yeah, will do.
Yeah, okay. So it's a question. Perfect. Thank you.
I have a question regarding the Smelly that you. So first of all, thank you for the presentation and the work. So regarding the Smelly that you presented, so how many of those do you think are due to the current state of the quantum computers? So the noisy computation of those computers, for example, the idle qubit could be a problem in the current era, whereas in the future the qubit state might be more stable, so the kind of Smelly that we have now could change perhaps. Did you have any feeling of how many are stable in time and how many are just temporary? Thank you. So
that's a very good question, thank you. So yes, so we identified 8 smells, and many of them are associated with the hardware limitation that we have right now. And many of them would actually go away. Now, to concretely answer your question, we actually haven't thought about that. Like out of these 8, which one are specifically related to the hardware and which are mostly related to humans' behavior. So we didn't dig deep into that, but obviously that would be an interesting area to look into.
Yeah, very good. Yeah, thank you.
Thank you.
Well, thank you so much. Great work. So now I have the honor to present my fantastic colleagues in telecommunication doing something I really like, cloning on C programs. So I can't wait to introduce this collaboration with York University and Weiwei, I guess both in Canada and in China. So welcome, Jinfu Chen. Oh, there you are. Yes, please. Yeah.
Yeah, thank you for the introduction. Yeah, hello everyone. So first, thanks for attending this presentation. And my name is Jinfu Chen, and now a faculty member of Wuhan University, and also happy the co-author Nemo Boyuan is also here. This work was done when I was working in Huawei, Canada, and this work is also collaboration with Zhang from York University. So first, let me introduce the background. Co-clones are the co-fragments which are identical or similar to each other, and the co-clones can be classified into 4 types. Here, I will not introduce the details. And why we want to detect the co-clones in industry, because the co-clones might propagate the bug, and it may also increase the software maintenance effort, and it can also introduce the recurring vulnerability, copyright, and plagiarism issues. Actually, many research have been proposed to detect the co-clones. These techniques can be broken into 2 parts: front-end data preprocessing and the back-end similarity detection. Actually, the front-end data preprocessing is responsible for the for parsing different kind of artifacts. So for example, the source code level or the compiler intermediate representation or the binary level. And also the front-end data processing, also maybe remove the uninteresting parts and convert the source code to a particular format. And the backend similarity detection will compare the similarity between two code fragments using different kind of techniques. Actually, there are many studies which report the effectiveness of different clone detection techniques based on the existing clone evaluation benchmarks. But fortunately, the existing studies suffer from the three main issues. The first issue is Java-centric, because prior studies, they mainly report the effectiveness of different kind of clone detection techniques running at the Java-based systems. And the second issue is source code-centric, because previous studies already compare the effectiveness of clone detection tools at the source code level. And the final issue is the number-centric, because the existing studies already quantitatively compare the clone detection results among different tools. And in industry, in Huawei, many of those products, they are written in C language. And currently, many different kind of code cloning tools used for different kind of tasks. However, there are few quantitative and qualitative analysis for clone detection set tasks applied on C-based projects. So therefore, we want to perform a systematic evaluation on the various clone detection set tasks, which means that different clone detection techniques, for example, the text-based, token-based, tree-based, and two types of the artifacts, the source code level and the compiler intermediate representation level. And our goal is to allow the developers and the industrial researchers to enhance the tool capabilities and provide some guidelines for them when to use and not to use certain type of tools. So to conduct our study, we first construct clone evaluation data set based on 5 widely used C-based open source systems. And in the second phase, we will conduct our clone detection experiments under 6 different set tasks, which vary depending on the clone detection techniques, text-based. We choose one representative text-based and token-based and the tree-based techniques on 2 different artifacts. And finally, we will quantitatively and qualitatively analyze the clone detection results among these different set tasks. So in the first phase, we want to curate a clone data set. We build our clone data set based on extending one existing clone evaluation benchmark, namely the CLUES benchmark. CLUES benchmark includes 3 C-based projects. We extend the benchmark on another large-scale C-based project. And in the second step, we will combine the selected projects to the LLVM-based representation using the C-LAN as the front-end compiler. And to ensure a fair comparison, we will similar to this prior study. We want to locate the optimal configurations for all the 6 different set tasks. And finally, we will construct our ground truth clone dataset. And in the end, we obtain a total of 791 clone pairs. And in the second phase, we want to perform the clone detection on the selected projects and output the results for further analysis. We choose 3 tools in our study, and namely NSFounder, SocialCC, and NICAP. Actually, NSFounder is included in our study because it's a text-based clone detection tool, for fast clone detection. And NSFounder is developed by Huawei developer and currently being used within Huawei. And the SocialCC and NICAP, they are 2 very popular clone detection tools. Prior research shows that these 2 tools yield great performance while applied at the source code level clone detection. And after we detect the co-clones, then we will post-process the clone results. We map the clone results reported by the IR-based setters to the source code at the master level. And then we will unify the formats. Our standardized format will contain each pair of the co-clones. They will contain the file path, file name, master name, and the position of the master. And in the next phase, we will conduct the quantitative and qualitative analysis. We follow the 4 steps to conduct our analysis. For the quantitative analysis, we first merge all the clones in the same techniques and at different artifacts, or in the same artifact, different techniques. And then in our performance assessment, we choose 3 metrics: precision, record, and F-score to evaluate the performance. For the record, we compare the clone results reported by each step of the clone detection against the ground truth clone evaluation dataset. And for the precision, to evaluate the precision, evaluating the precision is very challenging. To do this, we randomly sample a statistically significant number of clones. Then the first 2 authors of this paper will manually examine the sample of clone pairs to measure the precision. And for the qualitative analysis, we want to do this analysis on 2 aspects. For the first aspect is artifact dependent, and the second aspect is the technical dependent. Artifact dependent means that we want to understand the reasons why the clones can be detected only at the source code level or at the IR level. And the technique dependent means that why text-based techniques can detect the clones but mix in the token-based or tree-based techniques. So first, let me present the results of the quantitative analysis. Actually, we found that the 3 tools, they can achieve higher precision. But for the record, they have a large difference. In terms of the techniques, token-based techniques, actually in our study experiment, we choose the social CC. This token-based setup means the social CC, and are generally well-performing, while text-based setups achieve better precision. And in terms of representation, IR level setups are generally better than the source code level. And for the quantitative analysis, we identify 10 reasons why certain clones they cannot be detected at the IR level or at the source code level. And this is a total of 10 reasons. And due to the time limitation, I will just maybe present a few of the reasons. So the first reason is minimum line token. So after compilation, the number of the token or line of the IR instructions is smaller than the minimum token line threshold. And this is one example presented here, a clone pair in social CC at the source code level, but not in the social CC at the IR level in Linux kernel project. You can see that the source code, they are a clone pair in the social CC, but after compilation, the 2 methods both have 6 tokens, which is smaller than the token threshold. And the second reason is compiler inline function. The compilation, they can expand function inline, leading to the increased size of code. And this one, okay. Yeah, and found that this function in the source code, in the last method, is converted an inline function after compilation. And the next reason is the discrete size compilations can abstract the source code, leading to a smaller code snippet, and the similarity will be changed. And in this example, we found that this is a clone pair reported by the social CC at the source code level, but mixed at the IR level. The reason is that the similarity between the 2 methods at the II level, it becomes, I think 85% is less than our similarity threshold. And the next reason is the comparison optimization. Actually, this reason is very interesting. When we manually studied this, we found that the source code are the same in the Linux kernel project, but they are in different paths and different files. But after compilation, the IRs are different. So this, that is the reason. And the next one is the macro expansion. Macro expansions can expand or reduce the size of the source code. Then the similarity value will be changed. And the final one in this presentation is include expansion. The include expansion can add functions from the header or other source files, like the include statements in C language. I found that this code clones, it doesn't occur in the source code, but after we compile, we found that the two methods in these two files, they are code clones at the IR level. And finally, we show the discussions. As we found that the IR level, the chip-based NiCad performs the best in terms of F-score. And for the second part, the clone detection performance, because our prior study mainly consider the precision record and the F-score to evaluate the performance. However, in industry, we also care about the execution time of the clone tool. So I think more research is needed to further speed up the execution time. And the last one is the vulnerability detection. In industry, sometimes we cannot access we don't have the access to the source code, and we need IR level clone detections. Yeah, and that is my summary, and this is my name, Jinfu Chen, and this is my email. Okay, thank you for listening. I'm happy to take questions. Thank you.
Okay, maybe we have questions later, but very interesting work, I think, because it's important, as you say, in telecommunication and in C code, and to find these and understand the similarities. So now we move over to the short papers, and thank you again for the great presentation. Thank you. Yeah. So we now have 4 short papers, and we start with the journal first paper. And can I ask Daniel Oliveira to come here and present Developer Perception Matters? There you are. Machine learning so we will learn more about smells, right? 7 minutes, so it's perfect. Not much time.
Perfect. Hello, everyone. My name is Daniel Oliveira. I am PhD candidate from PUC-Rio, Brazil. And I'm here today to present our study, Developers' Perception Matter, Machine Learning to Detect Developers' Sensitive Smells. It's already known that developers constantly apply code maintenance activities. And during these activities, developers, intentionally or not, introduce code smells. Code smells are indicators of a deeper problem in the system and might be harmful. In this way, the literature defends that code smells should be removed as soon as possible, otherwise the removal will require additional cost and efforts. However, detecting code smell is not a trivial task, especially because developers often disagree about the existence of a smell. For instance, a developer can consider a method as a long method if it has more than 100 lines. On the other hand, another developer might only consider a method as long if it has much more lines than other methods from the same class. In this way, we can say that the existence of the smell is developer sensitive, once it depends on developers' perception. Those are the sensitive characters. Strategies to detect code smell can't consider the same threshold for all context or our developer team. So, in order to address complex and code smell detection and create detection rules more flexible, the literature proposed the use of machine learning as a promised way. The use of machine learning techniques allows strategies to learn from developers' example and adapt this strategy to their perception. However, it's unclear how the machine learning techniques behave in these scenarios of different perception from developers. That is, do machine learning techniques remain a promising way to detect the developers sensitive in a scenario of different perspectives? In order to answer this question and fill this gap on literature, we studied the accuracy, dispersion, and efficiency of 10 machine learning techniques when detecting 7 different smell types in a scenario of different perception of developers. A high accuracy indicates that the technique is able to properly detect the code smell instance. A high dispersion indicates that the technique is more affected by the different perceptions of the developers. And a high efficiency indicates that the technique is able to obtain a high accuracy with a low number of instances used at the training stage. To make sure that we are training the techniques using a dataset composed of code fragments with different developers' perceptions regarding the existence of a smell, we used the Fleiss-Kappa matrix. We are obtaining a low value of this metric, which indicates a low agreement between the developers used to classify our data sets. So some developers agree about the existence of smell in an instance, and other developers don't. We then selected code fragments where at least 2 developers disagreed about the existence of certain smell type, and we collected the software metrics from these code fragments and the different classification as smell or not by the developers to use it as training for the machine learning techniques. Finally, we ran the techniques and we observed that almost all studied machine learning techniques have statistically similar behavior in this scenario of divergence. We observed that only 2 techniques are statistically worse when detecting developer sensitive smells. In this way, we couldn't determine only one specific technique to be recommended for all smell types evaluated. Also, the techniques were influenced by developers' perception. Once, we observed that the accuracy have a higher dispersion when considering different developers individually. For instance, the same technique classifying the same smell type obtained a high accuracy for a developer and extremely low accuracy for another developer. And regarding the efficiency, we observed that most of the techniques are not directly affected by the number of instances. That is, the highest accuracy obtained by the technique was not directly related with a high number of trained instances because of the different perception used in our dataset. Finally, we observed that detection rules generated per developer tend to combine popular metrics found in the literature with several other metrics. For instance, the detection of the feature envy smell. The literature proposed the use of 5 different metrics, and during our study, we observed that when creating a detection rule per developer, the complete set of metrics includes all the literature ones and others not mentioned in the literature. Finally, when creating a unique rule for all developers, we only observe that some metrics from the literature still remain, and all the other metrics are also added. And this is just a summary. If you have any questions, feel free to ask.
Yeah, I think we can take the questions after. It's such a short time. Yeah. Thank you so much, Don. And now we are moving over to smells in testing from University of Luxembourg. Please welcome Sarah.
Thank you. All right, it's here. Hello, everyone. Welcome to this presentation on smells in system user interactive tests. My name is Sarah Hebshi. I work as a research scientist at Ubisoft. And today I'll be presenting work that was done when I was at the University of Luxembourg. It was mainly done by Renaud Rui Malika, who couldn't be here today. so you are stuck with me. All right. So we'll be talking about system user interactive tests, which are automatic tests that exercise the software application with a graphical front end. Generally, this kind of tests are black box, which means that they are not supposed to have a visibility on the system under test. Yet, one of their main challenges is to ensure synchronization with that system, because most of the time we are performing events on graphical elements, and we have to wait until we observe certain states. And finally, they are mainly maintained by QA teams, quality assurance teams, which do not necessarily have development background, and this affects the way they are created and maintained. So I can give you an example here, and we are lucky, like this screen is big, so maybe you can read something. But this is an example of a suit, which is written in Robot Framework, a keyword-driven testing framework. And as you can see, the test itself is written in natural language. And this is feasible because the keywords are defined later. So actually, the technical implementation and the actions are defined in the keywords, while the test itself only keeps the design specifications. And in theory, this should make the test more maintainable. So this study was done with our industrial partner, BGL BNP Paribas. It's one of the largest banks, I think, in the globe. And of course, as a banking company, they had very strict requirements, and they invested a lot in quality assurance. For a long while, their teams were actually testing the systems manually. The tests were done on web and mobile applications most of the time. And with releasing cycles getting shorter, they realized they have to automate some of those scenarios. And indeed, in 2016, they started automating and moving to Robot Framework. So now that they started automating their test scenarios, the QA teams could relax, right? Well, not really, because the system kept evolving, and with the evolution of the system, the suits had to evolve as well. And suits in particular, compared to other tests, they're very brittle because they are very tied to the graphical user interface. So sometimes you might move a button from a place to another, and a lot of tests are actually broken. It's not supposed to be like this, but the truth is that it's like this. So at some point, the team also realized that they need to invest as well in assessing and improving the quality of their test suite. And this is how this collaboration started. So when we wanted to tackle this problem, one first question that we asked was, can we rely on existing test smells in our study of suits? And to answer this question, I'm presenting an example, which is mystery guest. So this is a very famous test smell, especially at the unit and the integration level. And it's considered as a smell because the test is using an external resource file, so it's not self-contained. And what we found, surprisingly, is that in suits, actually using external resource files is considered very good practice because they like decoupling data from behavior specifications, and there is a whole thing about data-driven testing. So the point I'm trying to make here is that existing test smells may not generalize to suits. So in order to identify smells that are specific to suits, we followed a very classical approach with a multivocal literature review, nothing special here, and we covered both gray and academic literature. So we identified 35 smells in a catalog, and only 16 from them actually came from the literature. So the majority came from the gray literature, from discussions between developers and QA teams. And also 21 of them are actually unique to suits, so they do not apply to unit or integration testing. And I will try to give you some examples because I know sometimes it's very hard to visualize a smell. Here we have a first smell, which is sneaky check-in. So this smell happens when a test is hiding its assertions in actions that are at the wrong level of details. So instead of keeping the assertions at the design specification level, we are actually putting them at the implementation level, which of course makes the test difficult to read and also less maintainable. Another example is stinky synchronization. So this happens when the test is not using proper synchronization points. As I said in the beginning, synchronization is critical in suits. And if the developers are not using proper synchronization points and they are relying on waiting times, the risk is that the tests can become flaky, but also they might become slow and they slow the entire test suite. So here are your takeaway points or lessons. The first one is that the testing community possesses in-depth knowledge, especially about suits. And those suits have their unique issues, and I do believe that our community is not giving enough attention to this kind of tests. Also, if you check the paper, we are also covering or having a user study where we discuss these smells with people from BGL, and obviously not everyone agrees, and some of the smells are actually very subjective. Also, we have an empirical study on BGL BNP Paribas test base, but also open source projects, and we show that actually most of the smells are rarely refactored, which is, which aligns with what we have in the literature about smells in general. But what's interesting and maybe, less pessimistic is that generally when people learn about the smells, they actually avoid them in the future. Because we built a plugin that was adopted by the teams, by the QA teams, and even though they didn't go back, and refactored previous smells, they actually avoided introducing them in the future, which is not bad. Okay, finally, I want to grasp this opportunity to say that at Ubisoft, we are open for collaborations. If you want to apply your research on video games, please reach out. Thank you.
Well, thank you for the lovely introduction. Hello, everyone. I'm Yuekun. I'm presenting our journal first paper, Bash in the Wild, where we examined the language usage, some code smells, and bugs from real-world Bash scripts. This paper is co-authored by Zhang Li and I, Yung Tian, Chen Sun, Michael Godfrey, and Mei Nagapan. So what is Bash? Bash stands for Born Again Shell. It's both an interface to the system and a programming language. Users can use Bash to execute programs, manage files. Developers and sysadmins can write shell scripts in Bash to automate tasks. If you have used a terminal before, it is likely you'll be running on Bash. And Bash is popular. It is the default shell, the wrapper which users use to interact with the system, and the interpreter for shell scripts, which for many popular Linux distributions. And developers use Bash as a programming language. Developers write shell scripts, which are often in Bash. And we can see from GitHub that shell is the 8th most popular language, and it's still gaining in popularity. But Bash scripts are hard to write. There's a lot of gotchas. Sometimes just a missing or extra space can lead to bugs. In this slide on the left, we have hello-world, and that runs just fine. But if we change the string to hello space world, then it's buggy and it crashes. There's too many arguments for the left parentheses. So it's confusing. We need to have quotes around the variable x in order for the comparison to happen. And error handling is hard in Bash as well. Suppose if the make directory command fails in that first line, then the CD will fail. Changing the directory will fail, and then further commands will be done in the wrong directory and could result in unintended file deletions if they were cleaning up something. And that will be difficult to undo. So fixes for this could include adding explicit checks if the commands failed and exit the script for each one. Another fix is to add set-e, where Bash will exit on any error. But set-e has its own set of problems since it only checks under certain circumstances, since if statements is implemented in Bash as sort of quote-unquote errors. So to examine Bash usage in the real world, we collected 2 data sets using code search on GitHub and gotten a general data set with over 1.3 million distinct Bash scripts from 516,000 repositories. And also we collected a top 1K data set from the top 1,000 shell repositories to examine popular Bash scripts. We parsed all the Bash scripts and we collected and identified commonly used language features and utilities. We found between the top 1K and the general data set, the usages between the features and utilities are generally pretty similar. So hopefully the features and utilities we identified will be useful to others in future research. We also used shell check, a popular tool for checking shell script bugs. If you write shell scripts, Google's bash style guide recommend using it to check for some basic mistakes. Shell check found some broad categories of potential code smells in the bash scripts we collected. These categories, some regard coding, error handling, and return values. They're common in the general data set and slightly less so in the top 1K. We also manually inspected 200 bug fixing commits, 100 from these shell repositories, those 5 listed, with long history and large number of stars. We also inspected 100 bugs from the general data set. We found that bash semantic bugs are prevalent in the real world. We used open card sorting to find the themes of the bugs. 5 out of 57 were coding bugs. 8 out of 57 were related to files, path, directories. 6 out of 57 were from permissions. 6 were command options, and then 6 from error handling. We hope that these themes can help focus future research on bash scripts. And finally, everything we collected, the data sets, the data we collected are all publicly available for you to play with from that URL there, and it's also in our paper. Thank you.
How many do you use bash in the audience? So you should have a lot of questions too. So good contribution then. Cool. Yeah, cool, very much. Thank you, thank you. And we move on for the last paper in this session. Very intense learning. And we're gonna learn about similarity analysis last, right? So 1-to-1 or 1-to-n, and where is the author? There is no author. Oh, you're remote. Welcome.
Yeah, yes.
So, and you have your slides there?
Oh, yes. Oh, can you see the slides?
Yeah, please, go ahead.
Yeah. Oh, thank you. Hello everyone. My name is Zhang. Here I will briefly introduce our paper, 1-to-1 or 1-to-n, investigating the effect of function inlining on binary similarity analysis. Binary code similarity analysis is widely used for device security applications, including plagiarism detection, software license violation detection, and vulnerability discovery. And especially, most ICSE works use a 1-to-1 matching algorithm to calculate the similarities of two binary functions and carry out the downstream researches. However, we discovered that the function mapping is a more complex problem of 1-to-n or n-to-n due to the existence of function inlining. Thus, in this paper, we carry out the first study to evaluate the effect of function inlining on 4 security tasks, including code search, OSS reuse detection, vulnerability detection, and path detection. And especially, we raised the following 3 research questions. And the first is, to what extent will inlining happen during compilation? And the second is, what is the effect of function inlining on the performance of existing binary code similarity analysis works? And the third is, can existing inlining simulation strategies solve them? And before answer the above questions, we first collect a dataset and labeling it with the inlining to support our study. We follow the workflow of collecting source projects, comparing them to binaries, and identify the inlining in them to construct our dataset. Especially, we use BigKit to help compare projects in different architectures, compilers, and optimizations. And here we collect 4 datasets. We use dataset 1 for code search and dataset 2 for code reuse detection, dataset 3 for vulnerability detection and path detection, and dataset 4 will provide a vision of function inlining in large application binaries. After constructing the datasets, we will label it with inlining. To identify function inlining, we use the line mappings generated in the compilation we use in debug. For the source line, we use understand to find its mapped source function. And for the binary address, we use ID pro to find its mapped binary function. And finally, we aggregated the mapped functions by traversing our line mappings. Then we get all the function mappings of a binary from a binary to source. And simply, we can identify inlining by identify the binary functions that map to more than one source functions. So, through this approach, we can label our dataset with inlining. And after construct the dataset, we will first answer the first question, the intent of function inlining. We summarize the function inlining statistics in dataset 1 in different compilation settings at the left figure. And we use 3 metrics to evaluate the intent of function inlining. The first is inlining ratio, that is the percentage of binary functions with inlining. And the second is the number of inlined source functions per binary functions with inlining. And the third is the number of binary functions that one source function is inlined to. And according to the study results, we can find that inlining happens in high optimizations, and its ratio usually ranging from 30% to 40% when applying all 3. And a binary function is averagely inlined to source functions, and a source function is inlined to 2 binary functions. And then we answer a question about the performance of existing works. And here, due to the time limit, we select 2 study results. First, we select code CMR as a binary to source code search work. To analyze the impact of function inlining, we divided the binary functions into 2 classes, including the normal binary function that is generated by only one source function without inlining, and the binary functions with inlining. And through the results, we can say code search works suffer a 20% to 30% performance loss when detecting functions with inlining. And then we select Well-Seeker as a binary-to-binary vulnerability detection work. And apart from the normal binary function and the binary function with inlining, we have mentioned above, we also take another catalog of binary functions to evaluate the existing works. That is the binary functions which has inlined the vulnerable function. And according to the distribution of similarities of different classes of binary functions, we can see that OS's real detection and the vulnerability and patch detection works cannot detect the inland functions. And thus, attackers or plague readers can inline these risky functions into binary functions to bypass the detection. And the third, we answer the performance of existing inlining simulation strategies. And here we select 2 methods, including bingo and ASM2 vector. They have designed some rules to inline binary functions to simulate the function inlining during compilation. And these 3 cases are the designed rules, and we classified the binary functions into 2 classes, as the binary functions do not need to be inlined and the binary functions need to be inlined. We can observe that their most inlining decisions are conducted on the binary functions that do not need to be inlined. Their coverage are mostly above 17% to 60%. And here we can answer that the bingo and the ASM2 vector can help find the similar binary functions, but most of their decisions are conducted on normal functions. And when applying to detecting inland functions, it makes nearly 40% of the inland functions. And here is the end of our presentation. Thank you for listening.
All the way from Qian. Yeah, inlining is a very interesting result. I think we like to thank you for presenting, and I hope you're well. Wish you were here with us in this in the session. I guess you can contact him, right? It's possible to mail you and discuss in lining with you and the other authors. So thank you very much.